Assalamualaikum and hi. So in this video I'm going to explain the forced convection for internal. For forced convection internal, I divided it into 4 subtopics, which is the introduction, the entrance region, general thermal analysis, laminar flow and turbulent flow in tubes. And in this video I'm going to explain the introduction. Introduction, convection heat transfer. We have 3 types of convection heat transfer, which is free convection by buoyancy force, forced convection by pump or fan, convection with phase change by boiling and condensation. So forced convection by pump or fan, I'm going to explain the internal, the entry region fully developed, and we need to consider the existence of the entrance and fully developed regions, and we consider only the flow of laminar or turbulence. For internal flow, we have pipe, ducts, and tubes. And pipe is the circular cross section, duct is non-circular cross section, and tube is small diameter pipes with circular cross section also. So as you can see, figure 1 on your right hand side, we have a circular pipe, which is the circular cross section for pipe and also tubes, and whereas there is rectangular duct for duct, which been used for air conditioning and so on and so forth. So in the fundamental of fluid mechanics, the fluid velocity changes from 0 at the surface, no slip, to a maximum at the pipe center. As you can see on your right hand side, figure number 2, we have the VAVG, which is the average velocity. The dotted black line is the average velocity throughout the pipe, and then we have U as a function of R, which is the variation of velocity from the center of the pipe to the wall of the pipe. As you can see, we have the parabolic shape. So for these cases, it is convenient to work with an average velocity which remains constant in incompressible flow when the cross-sectional area is constant. An important parameter for internal flow is the average velocity. The value of the average velocity is determined from the conservation of mass principle, where mass flow rate in is equal to mass flow rate out. So from this fundamental equation, we can convert it into m dot equal to rho v average times the cross-sectional area. V average, rho is the density, equal to integration over cross-sectional area AC, rho times the U as a function of R dAC. As you can see here, V average is equal to integration over U as a function of R, which is U as a function of R is the variation of fluid velocity in pipe, as I put a note here. And then from this equation, which is I put it in blue rectangular, we can convert it into V average, as you can see for in the bottom equation, for incompressible flow in a circular pipe of radius R. So V average equal to integration rho U as a function of R dAC divided by rho AC here. So from this, we can convert the AC into pi r squared, as you can see in the equation. And from the conversion, we can remove the same parameter, which is the rho and pi. And then we can get the equation of 2 over r squared, integration over r to 0 for the function of u as a function of r dr. As you can see here, we have two kind of R, which is the capital R and a normal R here. So the capital R is the radius of the pipe, and it is a constant. And we have R here, distance from center of the pipe. So R here is the variation of distance from the center of the pipe towards the outer diameter of the pipe. Okay, another important parameter in internal flow is the average temperature. Okay, same with the velocity. We have variation of velocity in the throughout the pipe. Temperature also have a variation of temperature. As you can see in figure 1, we have Ts, which is the surface temperature. and T minimum is the minimum temperature of the fluid, which is located at the center of the fluid. And then we have the vertical dotted black line, which is the mean temperature or average temperature. So it is convenient to define the value of the mean temperature Tm from the conservation of energy principle. So the energy transported by the fluid through a cross section in actual flow must be equal to the energy that will be transported through the same cross section if the fluid were at a constant temperature Tm. So this is the equation where E dot fluid equal to m dot Cp Tm. M dot here is the mass flow rate, Cp is the specific heat, Tm is the mean temperature, and we can expand it to equal to integration over m dot, integration over mass flow rate, and Cp function of Tr delta m dot, and we can further expand it into integration over AC cross sectional area, rho Cp function of T temperature towards the R, and function of velocity U R times dAc. Here delta m dot is equal to rho time function of UR and dAc. So it is from the equation of m dot equal to rho VA, where m dot is the mass flow rate, rho is equal to density, and V is the velocity, and A is the area. Okay, for incompressible flow in a circular pipe of radius r, the mean temperature is equal to integration over mass flow rate, Cp, specific heat, function of temperature, the function of R, and delta m dot divided by m dot Cp. So the red rectangular here, this equation is come from the previous slide, as I shown in the red arrow, and then the equation, the red rectangular, can be expanded into the integration over cross-sectional area AC times Cp function of temperature times rho function of velocity 2 pi r dr divided by rho times V average times pi r squared times Cp, and the integration of cross-sectional area is get from the previous equation, as I shown in the green rectangular and green arrow here, and we can simplify this equation into the blue rectangular equation, which is the mean temperature is equal to 2 over V average time capital R squared integration over R 0 function of temperature function of velocity R dr. So you can calculate the mean temperature using this equation. So the mean temperature Tm of a fluid changes during heating or cooling. So as you can see in this figure, we have idealized and actual. In the idealized, we already changed the variation of temperature into mean temperature. So I put a note here. In the case of fluid properties, specific heat, density, thermal conductivity, which you need to find in the table in the internal flow, it is evaluated by bulk mean fluid temperature, which is calculated as follow, where Tb is the bulk mean fluid temperature equal to Ti is the inlet temperature of the fluid plus Te is the exit temperature of the fluid divided by 2. Okay. Laminar and turbulent flow in tubes. How do we know that the flow in the internal tube is in laminar or turbulent flow? We can know it based on the Reynolds number. For flow in circular tube, the Reynolds number is defined as the Reynolds number equal to rho, which is the density of the fluid, V average, which is the average velocity of the fluid, and D is the diameter of the pipe, divided by dynamic viscosity mu, and it is can be further simplified into V average, which is the average velocity, times D, which is the diameter of the pipe, and divided by the kinematic viscosity. I put a note here where mu is the dynamic viscosity and kinematic viscosity is V. For flow through non-circular tube, D is replaced by the hydraulic diameter dH, which is given here, where dH is equal to 4 times the cross-sectional area AC divided by the perimeter. So as you can see in the figure, rectangular ducts, we have AB, and from there you can calculate the hydraulic diameter. And in most practical condition, we set the laminar flow is below the Reynolds number of 2300, and transitional flow between the Reynolds number of 2300 and 10,000, and fully turbulent for Reynolds number above than 10,000. Although this is the most practical condition, but I put a note here. You should keep that in mind, that in many cases flow turns to fully turbulent for Reynolds number larger than 4,000 in most cases, and laminar flow can be maintained up to Reynolds number 100,000 provided that internal surface is smooth and by avoiding flow disturbance and tube vibration. Although this is a special case where you need to control a lot of things. And in our study, or in heat and mass transfer study, we will set the most practical condition as the laminar flow, transitional flow, and fully turbulent flow. Okay, so this slide is show the some sort of the summary of the introduction, where how do we calculate the Reynolds number for flow in a circular tubes, and you can convert the Reynolds number equation to mass flow rate equation. You can add in mass flow rate equation in the Reynolds number. And for flow through non-circular tube, the Reynolds number as well as the Nusselt number and the friction factor are based on the hydraulic diameter DH, which is given here, where DH is equal to 4 times the cross-sectional area AC divided by the perimeter. And as you can see on the right hand side, we have a few types of non-circular tube, square duct, rectangular duct, and channel. And we have this parameter A and AB, so you can calculate the hydraulic diameter. For circular tube, you can see here the hydraulic diameter is equal to the diameter of the pipe. And for the cases of the most practical condition, where the number of Reynolds number less than 2300 is a laminar flow, and the transitional flow is between 2300 and 10,000 Reynolds number, and for turbulent flow is above than 10,000 Reynolds number. So that's all for the summary. Okay, this is the end of first section of for force convection internal. Hope you guys enjoy this video, and thank you.